Okay, so number 20 out of 14.8 is really just this idea of show differentiability implies continuity. That's all there is. So to think about what's going on here, I need to remember what that continuity means. That's going to be my starting point. So maybe I look at continuity and think to myself, okay, when's continuity happen? Do you remember the criteria?
No.
Okay, so criteria for continuity are, you've got the limit x going to a of some function f of x is the same thing you get out of the function value. So the fact that I'm even writing this thing down, right, the limit and an equal sign, means that I'm saying that limit exists and that limit is this thing. And then I might spend a second and remember a better definition for continuity, which is really just to limit the definition of this limit. So for that, I need some quantifiers. So really what continuity means is that, well, continuity at a point A in a one-dimensional sense is for all epsilons bigger than 0, there exists a delta bigger than 0 with, let's see. Okay, so I need, if I'm delta off of A, right? So the absolute value of x minus A less than delta. So that means my x's are within delta of A, implies that the absolute value of f of x minus f of A, its absolute value, has to be less than epsilon. Okay, so what does differentiability have to do with this? Well, differentiability looks a little bit like this, but not exactly. Differentiability looks like if I've got the limit, maybe h tending to 0 of f of x plus h minus f of x over h. This goes someplace, specifically to f prime. Maybe let me unit these a's. Right? And so I see something a little bit similar here. Like, h is really how far off you are, right, from the point you're interested in. So I could really think about h as the absolute value of x minus a. And then a plus h and f of a, those are really playing this role, right? A plus h is kind of my x, and wow, f of a is exactly the same thing. So I'd like to start with this and just throw some absolute value bars around it. So if I just toss absolute value bars on both sides, look at this. I'm allowed to pull the absolute value bar through the limit because it's a continuous function. So really what this tells me is sort of, right? The idea here is that for small enough a's, f at a plus h minus f at a divided by how big h is gets to about the absolute value of the derivative in a. So my first step here is I'm just going to say, okay, that looks like the thing I want to control the size of. So I'm going to put the a over here, or the h over here. So really this is a little bit like saying, okay, having a derivative means that I can say the difference between f at a plus h and f at a is really about whatever the derivative is times how far you went. Does that make sense?
Yep.
Okay, so, and this is the part where quantifiers start to come into play. I want to say, okay, let me start with an epsilon bigger than 0. Right. So I need to show that for all epsilons there exists a delta smaller, bigger than 0 so that this stuff happens, right? So, okay, I'm going to let epsilon be bigger than 0, and now I'm going to, in terms of that epsilon, I'm going to supply a delta that works. So, the first things first, I know I can get close to this guy, right? I know that if I shrink h down, I'm going to get closer and closer to this statement being exactly true. It's never actually going to be exactly true, so I'm going to have to settle. So I'm going to say, since differentiability, right? So really citing this idea. There is a delta 1 with the difference between f at a plus h and f at a is less than or equal to, well, I know I can't quite get there, but I maybe can get to within a factor of 2. And I need absolute values. Okay, so all this is saying is there's a delta 1 with this stuff. Oh, and I need to really say when this is happening, right? So this is happening when absolute value of h is smaller than delta 1. So this is basically saying, okay, get close enough so you're within a factor of 2 of the derivative. And then we're going to say, okay, then there's also, oops, no, not that one. So, and this is the part where I'm going to actually define a delta because I've got a delta 1. I want a delta. Okay. This delta needs to make f at a plus h minus f at a small. Specifically, I would like to see this thing less than epsilon here, right? Okay, so to get this quantity less than epsilon, I need to make the absolute value of h smaller than, well, epsilon over this graph, right? Okay, so I'd like to say let delta equal epsilon over twice the absolute value of f prime and a. Well, but I'm not sure that that's smaller than delta 1, right? So maybe I should say, let's let delta be the minimum of this and delta 1. So we're going to get h smaller than delta 1, so we can write this sentence down. And then we're going to get absolute value of h smaller than epsilon over twice the derivative, so that I can replace this guy with epsilon. See that? Mm-hmm. So here's my delta, then, right, or therefore, the difference between f at a plus h and f at a is on the one hand, right, because I've got it smaller than delta 1, it's smaller than twice the absolute value of f prime at a times the absolute value of h. And then I know how big absolute value of h is. At worst, it's epsilon over 2 absolute value of f prime of a. And so I can put that bit in here. And now all this stuff cancels, right? 2's absolute values of f prime. So I get that this is actually less than or equal to epsilon itself. Cool. So the idea of differentiability implies continuity is just, hey, look, in absolute value, the difference between this thing at a little push off and my point I'm thinking about, that thing's controlled by the slope of the derivative. Mm-hmm. And so I'm just going to say, okay, well, let me double the slope of the derivative. And then say, okay, what the heck? I can definitely get it smaller than that. Like at worst case, near there, it's twice as steep, so you have to come in a little bit closer. And to do this in Calc 3 land, what do? What's the difference between the Calc 1 version and the Calc 3 version? This h then is going to be a little vector, right? Yeah, I'm really going to want to think about putting vector hats on everything. Is that going to make any difference at all? No. Only that here you need norm bars. But really that's it. So to do this in Calc 3, you just say, okay, I'm going to throw vector hats over the top of everything. This needs a norm bars now on h, because otherwise it's, right, I don't know how to take the absolute value of a vector, but I do know how to say how long it is. And that's really all we're going to do. We're going to run through this and add vector hats to everything. And really, probably, this f prime doesn't make a lot of sense anymore now, right? Right. Well, it's going to be the gradient now. So, go through and do those too. But that's all.